line equations for the cat were x is equal to -4 plus 2t, pardon me, and y is equal to 7 minus 3t, whereas the mouse, its trajectory was defined by the parametric equations x is equal to 1 plus t, and y is equal to -6 plus 4t. Pardon me. And yeah, so we just said, well, you know, let set the x for the cat equal to the x of the mouse and the y of the cat equal to the y of the mouse, and solve for t, and we found we got 2 different times for t, so it means they don't intersect. We did find the intersection point, and that was, what was it, 2 minus 2 or something like that. Yep, 2 minus 2. We did find this intersection point. And all we did to do that was we rewrote these parametric equations with different parameters. We used, for instance, s for the cat, and we used k for the mouse, so we decoupled them. Again, set x equal to x and y equal to y, and found the s and k values that made that true. And we found, in that case, we found s was equal to 3 and k was equal to 1. And when you put those values in for x, either the cat or the mouse, we found the x and y values to be 2 minus 2. And then we said, okay, well, what can we do to the cat so that it will catch the mouse? Well, one thing we can do is we can change its speed at which it's traveling along this trajectory, and either speed it up or slow it down so that it does reach this intersection point of 2 minus 2 at the same time as the mouse. And we can remember that when we have the equations for a line in 3D space, we automatically have 2 points, or pardon me, 2 pieces of information about that line. We have a point on the line, -4, 7 in terms of the cat. In terms of the mouse, we have the point 1, -6, not relevant to the current discussion. We also have a vector that's parallel to the line. For the cat, that would be 2 minus 3. The coefficients of the parameter. Whereas for the mouse, the vector parallel to its line would be 1, 4. Now we could interpret these vectors that are parallel to these lines as the velocity vector of the cat and the mouse. So we could say, well, this is the velocity vector of the cat. It has a direction, which obviously has to be the direction of the trajectory of the cat. We can't change that. But the magnitude of this could represent the speed of the cat. Maybe we can change the speed. Keep the same direction for this vector that's parallel to the trajectory of the cat, but change its magnitude, which means changing the speed of the cat. And we did that, pardon me, and we found that if we change the magnitude, so call this V1 old, we found V1 new. If we change it to 6 minus 9, in that case, the cat and mouse are going to be at the intersection point t minus t at the same time. Okay? And so all that means is that we've changed the line equation for the cat from x minus 4 plus 6t, y is equal to 7 minus 9t. Okay? It's still the same line in 3D space. Recall that for lines in 3D space, we can write an infinite number of parametric equations that represent that line. So it's the same line, it's just we've changed this vector that's parallel to the line. It's still parallel to the line, but it has a larger or larger magnitude, which means we've sped up the cat so it reaches this point at the same time as the mouse. That's what we did right at the end of the last day's lecture. Okay, well, is there something else we can do to the cat other than change its speed? If we go back to the original equations for the cat, the original equations for the mouse, what else can we do to change the fact that the cat is not going to reach the mouse with these original equations? For the cat to catch the mouse, well, one thing we did was we changed this velocity vector. The other thing we could change is the initial point. You can think of this as the initial point of the cat when time is equal to 0, right? When we put t equal to 0 in here, our parametric equations for the cat give us -4, 7. So maybe at time, at time t equal to 0, that means the initial point of the cat is -4, 7. When time is t equal to 0 for the mouse, it is at, its initial point is equal to 1 minus 6. Right? We get that from the parametric equations. When t is equal to 0, x is equal to 1, y is equal to -6. Well, maybe we could change the initial position of the cat. I don't know, since we had to speed up the cat for it to meet. If we go back to the original speed of the cat, well, maybe we have to make the initial point here for the cat. Okay, still the same line in 3D space, but now we're going to change this initial point where the cat starts. Okay, well, let's just rewrite again. Instead of these parametric equations, now we're going to write x is equal to some new x naught plus 2t, y is equal to some new y naught minus 3t. Okay? Still the original equations here, we're just going to change this point on the line to a different point on the line. It's going to be our new initial point when t is equal to 0. But it's still a point on the line, it's still the same line. Okay, and we still got the original equations for the mouse. X is equal to 1 plus t, y is equal to -6 plus 4t. Okay, we still know that the intersection point is 2 minus 2, right? We still have the same two lines, which means they still intersect here. Okay, and that's where the cat's going to catch the mouse, where they intersect. Okay, we also know that what? That if we put that point into the mouse equations, 2 minus 2 plus t minus 6 plus 4t, when does the mouse reach that point? Obviously when t is equal to 1, right? Okay, so we know the mouse is at point 2 minus 2 at a time of 1. The cat needs to be at the point 2 minus 2 at the same time, at a time of 1. Okay, so we take our cat equations. Cat's got to be at an x-coordinate of 2 and a y-coordinate of -2 at the time t is equal to 1. Okay, solve for x naught, what do we get? Looks like that's 0. And what do we get for y naught? Looks like y naught is equal to 1. Okay? So that's another thing we can do. We can rewrite the equation of the cat. We can give it a new initial point when t is equal to 0 in order to make sure that when t is equal to 1, the cat is also at the intersection point at 2 and -2. Okay, so that's it. Any questions about anything we did there? Okay, that's just playing around with lines in 3D space, just so that you understand. Again, there's two pieces of information in that line. There's a point on the line, and there is a vector parallel to the line. Okay, whereas with a plane equation, and remember with the plane equation we've got, with the plane equation, it looks like this. Okay. There's two pieces of information in the plane equation. There is a vector perpendicular to the plane with the components A, B, and C, and there is a point on the plane which is encompassed by this parameter D. Okay, so really, what have we done in the course so far? We reviewed vectors, and we focused on three important things with vectors. The dot product, and an important application of the dot product is the projection of one vector onto another. And we've got the cross product. Okay, the dot product gives you a scalar. The cross product gives you a third vector that's parallel to the plane containing the first two vectors, according to the right-hand rule. Okay. We looked at the plane equation, and we've looked at now the line equation. Those are sort of the big parts of the course so far. Okay, so at the end of the lecture notes on line equations, right at the last page, there's a list of possible questions we could ask you having to do with lines, right? We could ask you to find the line equation if we give you a point and a vector parallel to the line. Well, that's really easy. Or we could ask you to find the line equation if we give you a point and a line that's parallel to another line. Or if we give you 2 points on the line. Or if we give you 2 plane equations and ask you, well, what is the equation of the line which forms the intersection of those 2 planes? And a bunch of other ones there as well. So make sure you have a look through that and think about, well, what would my strategy be if I was given 2 points on the line, how would I figure out what the line equation would be for that line? Okay, so that's a good exercise for you to do, to see, because basically, you know, what kind of questions we could ask you about lines, they're all listed there. Okay. All right, so that takes us to the end of lines. So we know a plane equation and we know line equations. Okay, so now let's talk about our next topic, which builds on these concepts. When we talked about the line equation, we talked about parametric equations. So let's keep going with that, and let's generalize it. Lines are specific examples or a subset of just general curves in 3D space. So if we've got 3D space like this, we could have some curve in 3D space. Up till now, our curve has been a straight line, but now we're just going to generalize it. Well, how do we represent a curve like this? How do we write down a mathematical equation for it? Okay. So we've got some type of curve C, and we're going to use a parametric equation to do it, just like we used a parametric equation to represent a line in 3D space, because a line is just a special case of a curve. Okay. And we're again going to use a position vector to do that. A position vector, we're going to call them R, always starts at the origin, and a position vector, the tip of the arrow, is going to trace out this curve as the parameter t changes. T might mean time, it might mean something else. Time is easy to think of. So at some particular point in time, the position vector is going to look like that. Call that RT1. At some later point in time, the position vector is going to look like that, RT2. Okay. Excuse me. At some other point in time, it's going to look like that. Call it TN. Okay, so as T changes, this position vector, which always starts at the origin, the tip of the arrow is going to trace a curve through 3D space. So obviously the position vector is constantly changing in direction and magnitude. So some point on here is going to have functions x, y, z, which are going to be also functions of this parameter. As t changes, x, y, and z change, we get a different point on the curve. Okay, so this position vector r, which is going to define this curve, we say it's a vector function of t. Vector. Wow. Where did I get that spelling from? It's a vector function of t. Okay, it's a vector function because it gives you a vector for a particular value of t. You put some value of t in here, you get a vector out. The vector that points from the origin to the curve at that particular value of t. okay? So when we talked about a straight line, our position vector, so if we're talking about a straight line, which is a special type of curve, our position vector looked like this. And we wrote this way back when we talked about lines at the beginning. It's the sum of a position vector that points to a point on the line plus another vector times t, okay? And this vector v here was the vector parallel to the line. So that was for our straight line, which is simply x naught plus t v1, where v1 is the x component of this vector v, y naught plus t v2, z naught plus t v3, right? So x equal to this, y equal to this, and z equal to this are just our parametric equations for a line. But we can write it in this vector, or in this position vector notation. Okay. So that means we're not just limited to straight lines now in 3D space. We can have any curve in 3D space. And we can use parametric equations or a parametric representation to define it or write it down. So let's look at some examples. Now for a lot of these curves, there is no turn the crank method to generate the parametric equation for the curve. You have to think about it yourself. And in many of these curves, there's a lot of different parametric equations you could write to define the same curve, okay? So there's a little bit of an art to figuring out, well, what's the parametric representation for this particular curve? Okay, well, what about this example? Find the parametric equation for curve C, that is the intersection for two planes. The intersection of two planes. So we've got one plane equation, x minus y plus 2z is equal to 4. We've got 2x plus y minus z is equal to 2. Two plane equations, somewhere they presumably intersect. What is the parametric equation for that? Well, what kind of curve is the intersection of two planes? It's a straight line, right? If you have two planes that intersect with each other, they're going to intersect along a straight line. So we know already that we're looking for a straight line. And we already know what the parametric equation for a straight line looks like, right? Okay, well, what we need is we need equations for x, y, and z that are a function of some parameter, call it t. You can call it whatever you want, but we typically use t. Okay, well, we need x is equal to some function of t, we need y is equal to some function of t, and we know z is equal to some function of t. And all we got are these two plane equations, where they intersect. Okay, well, again, it's a straight line in 3D space. There are infinite number of parametric equations we can write for it. So that gives us some choice. We could just say, well, I'm gonna make the z parametric equation dead easy. I'm just gonna say it's equal to this. Okay, so that means this third parametric equation is just equal to t. I could have said let x equal to t. I could have said let y equal to t. I could pick any one of those three and say, I'm going to let it just be equal to t. Okay, well then what do my plane equations become? Well, they become x minus y plus 2t is equal to 4. And they become 2x plus y minus t is equal to 2. Okay, so now I've got two equations and I've got two unknowns x and y. I want to solve them because I want to end up with an equation that's just a function of t and a second equation that's just a function of t. Well, I got two equations, two unknowns, solve them. Gauss elimination or substitution, whatever method you want to use. And when you do that, you're going to find x is equal to 2 minus 1/3 t, y is equal to negative 2 plus 5 over 3t, and we started with z is equal to t. All right, and there are my parametric equations for the line that is going to be the intersection for those two planes. I can double check my work simply by putting each one of these value expressions of t back into both of these plane equations for the values of x, y, and z. Right? You put these expressions for x, y, and z in this equation, and it should satisfy it. You should put the same equations for x, y, z in terms of t into this second plane equation. It should satisfy it. If it doesn't, you know you've made an error. If it does, well then this is going to give you the line which satisfies both of these. It's the line of an intersection. And again, I could have started with y is equal to t, in which case I would get different expressions for x and z as a function of t. Or I could have said let x is equal to t, and I would get different expressions for y and z using the same method. Or I could have said let z equal to 3 times t, or z is equal to 5 times t, or negative 9t, right? I can make z whatever I want, and then from then on, that'll dictate what the expressions for x and y have to be in order to satisfy these equations. All right. Any questions about that? Okay, so straight line we already know. Let's look at something a little more interesting. Let's say we have a circle. X squared plus y squared is equal to a squared. And we want to write the parametric equation that represents this circle. I'm a bad circle drawer, but that's approximately a circle. And obviously it has a radius of a. Okay, well, often the best way to figure out what the parametric equation is for some curve is to imagine a point on the curve and it's moving along this curve. So the curve is really the trajectory of some point. So we've got some point P here, and maybe it's going around the circle in a counterclockwise fashion. Okay, maybe it starts at this point A here on the x-axis, which obviously has coordinates of A0. Okay. And we can assume, again, there's an infinite number of parametric equations we could write to define the circle, so we can make pretty much any assumption we want. We're going to assume that it starts at this point at a time t equal to 0, and it moves in this direction counterclockwise with an angular speed of 1. Moves counterclockwise with angular speed of 1. Okay, well, what are the coordinates x of t and y of t going to be equal to for this point as it moves on the circle? Well, whenever you see a circle, you should be thinking trig, right? So if we take this point P, this general point P right here, well, it has this x-coordinate, right, and it has that y-coordinate. And if you'll remember a circle, the x and y coordinates are defined by cos and sine functions, right? We have a right angle triangle here. So the x-coordinate is given by cos. It's got a radius of a, and the y is simply sine. Okay, so when t is equal to 0, and sometimes it's a little bit of a guessing game. You just kind of got to figure out, well, I think these might be right. Now try it out. Okay, when t is equal to 0, what do I get here for the x? Well, the cos of 0 is equal to 1. I get 1 times a, where a is the radius of my circle. So that would be this point right here, right? X value of a. At the same time, t equal to 0, well, sine of 0 is 0, so y is equal to 0. 0. Yep, that makes sense. These parametric equations will give me this point here, a, when time t is equal to 0. Okay, what about when time t is equal to, let's say, up this point up here at b. We know at b, what are the coordinates? They're going to be 0, a. Okay, well, what about when time t is equal to pi by 2? I shouldn't say time. It doesn't have to be time. In fact, in this case, it's more helpful to think of t as an angle, right? When t, the angle is 0, I'm down here. When the angle is pi by 2, I'm up here. Okay? Well, at that case, what's the cos of pi by 2? Is 0. What's the sine of pi by 2? Well, that's 1, so I get a. Okay, so it looks like it works. And you can keep trying for other points to make sure that at different values of t, which you can interpret to be this angle here, right, that's our t, these equations will give you the correct coordinates for x and y on this circle. Okay, so there we go. There's the parametric equation for a circle of radius a. Is that the only parametric equation that we can use for that circle? Well, absolutely not. I could also write this. Right? That'll work too. It just means that the angular velocity of a point traveling on the circle would be 2 instead of 1. But it'll still give me the same circle. Right? So that's legit. Or cos 3t sine 3t. Or cos negative 4t sine negative 4t. Right? Doesn't really matter. It'll all give me the same circle. And you can always double check by taking these expressions and substituting them back into the algebraic representation for the circle, right? Doesn't matter if x is equal to this or x is equal to this and y is this and y is this. You square this, add it to this, square of this, you'll get a squared. You square this, add it to the square of this, you'll get a squared. So you can always double check. Okay, and we could say, well, instead of, when we write our parametric equation, instead of assuming that our particle starts here and goes like this, what if our particle started up here instead, and again went clockwise? Along the same circle. Let's make it a little more general, make it a little more useful. With an angular speed of omega. Well, then our parametric equations are going to be x of t is going to be, again, a cos of something sine of something. Okay, that will describe the same circle. It's just the assumptions, if we think of the circle being a trajectory of a moving particle, have changed. We got a different starting point. We're starting at B, right? We can double check. Okay, when t is equal to 0 here, we get the cos of pi by 2. Well, the cos of pi by 2 is 0, so we get an x value of 0. That's correct for point B. And if we substitute t equal to pi by 2 here, pardon me, t equal to 0 here, we get the sine of pi by 2, which is equal to 1, which gives us a y value of a. Correct for point B. Okay, and then you can try it for different values, for different values of t as we go around the circle to make sure you get the right coordinates. Okay, and you can rewrite these a little simpler, right? This is really equal to negative a sine omega t. And this is really equal to a cos omega t. And if you're a little unsure about what we call phase shifts, right? This adding of pi by 2 here, we call that a phase shift. And if you go into electrical engineering especially, you got to be very familiar with these. So let me give you a little hint about how you can simplify from something with a phase shift to an expression without a phase shift. Okay, let's start with this first one here, a cos omega t plus pi by 2. Well, what does that look like? If I would plot that, this is a cos function, right? The magnitude of a minus a here. that would be cos of omega t. Okay, well, if I now introduce a phase shift of positive pi by 2, maybe I should write the angles on here too. This is pi by 2. Oops, pi by 2. This is pi. This is 3 pi by 2. If I now introduce to this cos omega t a phase shift of plus pi by 2, the way I remember that is I grab that cos with my two hands like this. Okay? So your right hand would be somewhere on the positive omega t axis. Your left hand would be somewhere on the negative omega t axis. And now I push with my right hand, which is on the positive omega t axis, because this is plus pi by 2. So I grab my cos omega 2 function and I push it with my right hand like that. Okay? If I do that, and I push it by an angle of pi by 2, if I do that, what am I going to get? Well, that means this point here is going to end up pi by 2 over here. So my cos now looks like this. I'm not very good at drawing, I'm sorry. Let's try that again. I didn't draw this to scale. It's going to look like this, then it's going to look like this. Okay? If you take the black cos omega t curve and you push it with your right hand, which is on the omega t, positive omega t axis, you're going to push it in this direction. And you push it by pi by 2. So now we end up with the red curve. Okay, that red curve stands for this cos omega t plus pi by 2. Okay, well, what is the red curve in terms of sine? Well, we know that sine looks like this. So what's the relationship between the red curve and the blue curve? Well, they're just the negative of each other, right? And since the red curve stands for cos omega 2 plus pi by 2, it must be the same as the blue curve, but it's negative. Pardon me. Let me say that again. Cos omega 2 plus pi by 2 is the red curve. And the red curve is just the negative of the blue curve. And what is the blue curve? Well, the blue curve is sine omega t, right? Which means that the red curve is just the negative of the blue curve, which is negative sine omega t. So that's how I know it's negative a sine omega t. I take my cos omega t, which is the black curve, I grab it with both hands and I push with the right hand, which is on the positive omega t axis, I push it by pi by 2. Okay, that turns the black curve into the red curve. Now the red curve is my cos omega t plus pi by 2. And that is actually the negative of a sine. So I can just write negative sine omega t. Okay? I can do the same thing with this one here. I'm going to have to draw another picture. Okay, we start off with sine omega t, because we've got sine omega t here. Forget about the phase shift, just sine omega t. Okay, well that's easy. Sine looks like this. Okay, I grab my sine omega t curve with my right and left hand, and I push with the right hand, which is on the positive axis. If this was negative, I'd push with the left hand, which is on the negative axis. But because the phase shift is positive, I push with my right hand, and I push it by pi by 2. So what do I get? I get, I'm going to use red. So now I get this. I hope that's about right. Not very good, sorry. Okay, so now the red curve is my original sine omega t plus pi by 2. Okay, so this red curve represents the sine omega t plus pi by 2. And what is that? Well, that's obviously a cos, right? So I can just write a cos omega t. All right, so that's just a way that you can figure out how these phase shifts work. Hopefully that's useful to you. Okay, so in the lecture notes, there's a couple more examples of different, what if we write the parametric equation if we assume that we start at point B and instead of going counterclockwise, we go clockwise. Okay, well that just means this is going to be a negative omega t and a negative omega t. Okay, what about, so you can look at that yourself, work through that yourself. What about this circle? Let's go to black. X minus x naught squared plus y minus y naught squared is equal to a squared, where x naught, y naught is some particular point in space. Well, obviously this is a circle, but it's not centered at the origin, right? Well, in that case, without a whole lot of thinking about it for too long, right? If you think about it, we're just dealing in 2 dimensions here just to keep things simple, right? But let's say x naught, y naught is right there. And our circle looks something like this. Well, obviously the x coordinate of any point on here is going to be this distance plus whatever the circle equation would give you, right? So this distance, x naught, plus, again, if t is equal to 0, we would get a cos of 0 is 1, 1 times a is a. So when t is equal to 0, we would get an x value of x naught plus the radius right there. When t is equal to 0, sine of 0 is 0, our y coordinate would be just y naught, right? So we would be there. Okay, so again, sometimes when you're asked to write the parametric equation for a curve, it's a little bit of thinking. Again, there's no turn the crank method, there's no formula or anything like that. You just have to think about, often it's easiest to think about if a particle was traveling, how would I describe its trajectory? Okay, any questions so far? Okay, so what about this? And again, you can always double check your answer. If you write something down and you say, I think that that's what might be it, you can always try it out. Just take this expression for x and stick it right in there. And this expression for y and substitute it for y here, and then see if this equation is satisfied. If it is, you've got the right answer. If it isn't, well then you've made a mistake. You can always double check your work. Parametric equation for the ellipse okay, well now we've got an ellipse. We don't have a circle. But the equation is going to be similar, right? X is still going to be some function of cos of t. Y is probably still going to be some function of the sine of t. Okay, but we don't have a perfect circle now, so the radius might be different. Well, what if I make the radius for xa, this a here, and I make the radius for yb? Okay, and then I say, okay, well, I'm going to double check. Take a cos t and put it in here for x. Take b sine t, put it in here for y. Does it satisfy the equation? And yes, it does. If you got these backwards, if you wrote b up here and a here, then you would find that out when you put these back in for x and y that it doesn't work. And then it would have been obvious. Excuse me. Would have been obvious pretty quickly to you what you did wrong. Okay? Okay, what about this one? Okay, again, I want an equation for x equal to some function of a parameter, call it t, and I want a second equation, y is equal to some function of t. And we all know what this parabola looks like, right? That's y is equal to x squared. Okay, I want equations for x and y that are a function only of t. Well, I could just say, let x equal to t. And now what does y have to be? Somebody want to shout it out for me? If I say x is equal to t, then what does y have to be?
T squared.
Exactly. It's that easy. Okay? What would be my position vector as a function of t for this parabola? T squared, right? Or t I hat plus t squared j hat. Okay, well, I'm an electrical engineer, so I don't know exactly how all this manufacturing stuff, that's for the mechanicals and the manufacturing engineers to know. But I suspect that when you're machining a part, and if you have a computer operating the saw or the drill or whatever tool, and you're machining some part that has a parabolic shape to it, my guess is that there's a computer, controlling the saw, for instance, and it needs to run, that computer program needs to position the saw to make this cut. It could possibly use some sort of parametric equation like this to do it, and it just varies t from one value to another, and this will give it the coordinates for, it'll give the coordinates for where the saw should be at any particular point in time. Okay, I don't know if that's exactly how it's done, but I'm guessing it's something similar to that, right? So being able to write a parametric equation for any curve in 3D space is very, very useful in some fields. Okay. Okay, what about, let's look at something a little bit more interesting. How about a circular helix? And now if I think I might have a picture for it. Let me just see. I do. So that's what we call a circular helix. It looks like a spring, okay? And if you want to write the parametric equation for it, well, now we've got a three-dimensional curve. So far we've only been looking at two-dimensional curves. Now we've got a three-dimensional curve. Obviously there's an x, y, and a z component. Okay, well, if we, z is up, right? Yeah, this would be the z. And this doesn't matter, but I should get it. I should get it right for the first one too. Doesn't matter, but if that's z, then this would have to be x and this would have to be y. Okay, if we just look in the xy plane, what do we got? If we look at this curve straight down in the xy, on the xy plane, what would we see? We just see a circle, right? So in terms of x and y only, the parametric equations would just be the parametric equations for a circle, which we already know, right? So we've got some r of t, so some position vector, again, which is always going to start at the origin, which is right down here, right? There's the origin. So this position vector is always going to start at the origin, and the tip is going to point to a point on the curve. And so it looks like the starting point here. So initially when t is equal to 0, the position vector points like this. When t is equal to 1, maybe like this, t equal to 2. So it's going to be tracing out these coils of this helix. As t increases, it's going to get higher and higher and higher up on the spring, if you want to view this as a spring. But in terms of x and y, it's always going in a circle. Okay, so we already know what those are, but now in this case, the direction we're not going counterclockwise when looking from above, we're going clockwise. So x is actually going to be a sine t, and the y is going to be a cos t. Okay, and what is z going to look like? Well, as t increases, in the xy plane, we go around a circle. Okay, at a constant angular velocity. As we go around the circle, we're going to be increasing in z, right? And it's going to be a linear increase in z as we're going around. Okay, if you looked at this helix from the side, what would it look like? Oh boy, it's going to look something like this, right? I imagined it like switchbacks going up a mountainside. Okay, and every time we go around, you go up a little bit in z. Okay, but it's going to be a linear increase in z. So it might be just something b times t. Okay, the larger b is, well, the larger the gap between coils in my helix. Right? If I make b a large number, that means z increases very rapidly as I go around the circle once. If I make b very small, then the coil spacing is a lot smaller. Okay, we actually call that the pitch of the helix. All right, and we're out of time, so we'll stop there. We'll do one more example when we meet on Wednesday. Okay, so that's parametric equations for curves in 3D space. All right, I'll hang around for a couple of minutes if anybody has a question. If not, we'll see you on Wednesday.